Good morning, everyone. Today we are very happy to be able to invite Miss Foteine Dimitracopoulos, who is a PhD student at the University of New Mexico at this famous Institute of Meteoritics to talk about Mars. So we are going to Mars today, and her title is Mars Exploring the Red Planet with the Curiosity Rover. As you can see, can you guess what Foteine could be? And I give the answer. She is, so I say half Taiwanese and half Greek, right? And she would tell you something about herself in her name in Chinese, and her interest, in Mars, and later on, she will talk about her study, the data, I suppose the data analysis of observation using the instrument called LIBS, which is a laser-induced breakdown spectroscopy. Yeah, and that's all very, very interesting new development because the rover is still working and running, and they're searching for life. So I will let Foteine start her talk. Thank you, Foteine, please.
Hi, good morning. Thank you so much. So my name is Foteine Dimitracopoulos. My Chinese name is Di Ruoshi, and my research is actually about calibration for the ChemCam instrument doing laser-induced breakdown spectroscopy. And I'll talk a bit about it in this presentation. So let's get started. Do that. There we go. All right. So I'm going to start us off with a brief introduction about Mars. So it's one of the terrestrial planets in our solar system inside the asteroid belt. It is the fourth one from the sun at a distance of about 227.9 million kilometers or 1.5 AU. It has an axial tilt of 25.2 degrees, which is very similar to that of Earth right now. However, the Martian obliquity has actually changed quite drastically throughout the planet's history, and this has had a significant effect on the climate on Mars. It takes about 687 Earth days to orbit the sun, and each Martian day lasts a little bit over one Earth day at about 24.63 hours. So Mars is known as the red planet due to significant quantities of iron oxide in the rocks. It is roughly half the size of Earth, and it does not have plate tectonic activity. But we have had investigations into Mars seismic activity, and studies indicate that the general structure of present-day Mars is as follows. We've got a solid, mostly iron core, a thick mantle of silicate rock, and a thin rocky crust, all hidden in there. Now, it has two small moons. It's got Phobos and Deimos, which are thought to be either asteroids that have been captured in early Mars history, or that they are the remnants of a giant impact event. Mars also has a thin atmosphere that's composed mostly of carbon dioxide with trace amounts of other gases such as nitrogen and argon. Now, the average pressure at the surface is about 6 millibars, or 0.6% of the atmospheric pressure on Earth. And despite how thin the atmosphere is, Mars still has dynamic weather systems forming clouds, strong winds, and dust storms. But just as Earth has its own history that is divided into eons, so too does Mars. So the historical periods are the Noachian period, which lasted from formation at about 4.5 billion years ago to 3.7 billion years ago, and it's characterized by volcanic eruptions and an accumulation of water at the surface. Next is the Hesperian period, which is 3.7 to 2.9 billion years. And it's characterized by a slowdown of geological activity and change to colder, drier conditions. And finally, we have the Amazonian, which is 2.9 billion years to the present day. And it's characterized by aeolian activity that continues to shape the Martian surface today. So moving on, Mars has played a really significant role in cultural history from its representation as different gods and varying omens in ancient Greek, Roman, Hindu, Egyptian, and Chinese mythology. And its role evolved to be more of increasing scientific interest as our knowledge of the solar system expanded and as technology improved, and we began to get a better idea of what Mars looked like. And this inspired imaginations and sparked the idea of extraterrestrial Martian life. Now, Mars is of particular interest to planetary scientists and astrobiologists alike, as we strive to understand more about objects in our solar system and learn more about the history of Mars and the similarities and differences that it has to Earth, and to try to determine a past habitability, the presence of organics, and search for biosignatures to look for evidence of life beyond Earth. So here is a family tree of sorts of missions to Mars. And since about 1960, we've sent more than 50 missions to Mars, including flybys, orbiters, landers, and rovers. And this has been an international and collaborative effort to map and investigate the surface of Mars and track the changing environmental conditions. So with some more missions to Mars, we were able to learn even more than Earthbound observations. So I'll go through a couple of really significant discoveries that have been made, some generalized discoveries. So first are volcanoes. Most of them are in a region called the Tharsis region, which is mostly covered by this image I've got in the background here. And this region includes the largest volcano in the solar system, which is Olympus Mons, which is right under the D in the discoveries in the title. Now, volcanic behavior is really different on Mars in comparison to Earth because of different physical parameters. So for example, since Mars has a lower gravity, it allows for longer, more widespread lava flows. And in addition, we can have greater quantities of ash erupted higher into the atmosphere than on Earth. So next, we have some discoveries about ice caps at both the northern and the southern poles of Mars. Now, the background image here is the northern ice cap on Mars. And these ice caps are actually composed of a mix of water ice and carbon dioxide ice. And due to the obliquity of Mars, there is some fluctuation in the quantity of CO2 ice. Both of these poles, they have a variety of surface features. So one example is in the South Pole, where we have features called spiders. And these are thought to be the result of when the CO2 ice sublimates and the CO2 gas accumulates at the bottom of that layer of ice, and then it bursts out in the weak spots and carries all of this dust with it. So another really major discovery on Mars is evidence for extensive fluvial activity across the planet. So some notable examples include fluvial channels and delta fans, inverted channels, and even geochemical evidence for aqueous alteration. Water was really widespread on Mars. In fact, there is an idea that there was a very large ocean at one point. And this has implications for understanding habitability early in Mars history. So in these images, in the background, the large image is of the delta in Jezero crater, where the Perseverance rover is today. And on the right-hand side, we have some channels in Chrysi Planitia, a channel in the Tharsis region, and also some outflow channels in the Jovis Tholis region. So this leads us to Gale crater, which is where Curiosity is today. Now, that black oval that we see here, you can see my mouse, that is where the Curiosity rover landed. Now, Gale is about 150 kilometers across and about 5 kilometers deep. And it has this central mound called Aeolus Mons, or more commonly known as Mount Sharp. And this Mount Sharp is 5.5 kilometers above the crater floor. So Gale was formed roughly around the end of the Noachian period, beginning of the Hesperian, around 3.6 billion years ago by a really massive impact event. And this impact event generated enough heat to sustain a lot of hydrothermal activity for at least a few 100,000 years. And in addition, a lake was formed. And this lake persisted until the environmental conditions became colder and drier. And evidence for this kind of activity can actually be seen in the sedimentary rock layers and in hydrated minerals. So, Curiosity was sent to Gale with several scientific goals in mind. Mainly, we want to assess the biological potential of Gale Crater. We want to investigate the geology and the geochemistry of the environment along the Rover Traverse. We want to better understand the evolution of environmental processes of the water, the atmosphere, and the climate on Mars, past and present. And lastly, we want to characterize radiation levels and hazards, which is information that will be useful for future missions. But most importantly, Curiosity's primary goal is to explore and quantitatively assess Gale Crater as a potential habitat for life in the past or even the present. So here we are. This is the landing site for Curiosity. Curiosity landed on August 5th, 2012, and this location is called Bradbury Landing. And from here, we're able to see Mount Sharp up in the distance here. So this next slide is that zoomed in bit from that little rectangle from the previous slide. So this image was taken on Sol 23 of the Traverse. And real quick, a Sol is a Martian day. And this count, it begins from the first Sol of operations at the surface. So here, in this image, we can see the layered sedimentary rocks of Gale Crater quite clearly. We've got the crater plains, and then we have the dune fields, the hematite unit, the clay-bearing unit, and a magnesium sulfate unit on top of all of that. Now, these rocks hold a record of not only Gale's history, but also Mars history and habitability, as well as the changing environmental conditions dating back 3 to 4 billion years ago. So it's like a window into the past, so to speak. So here's a depiction of Curiosity's journey from Bradbury Landing all the way to the Geddes Vallis Channel. And we've gone around up here, around the Yardang unit, and we are going to an area called the Boxworks. We have marked 4,633 sols of operation and counting. And as of mid-2025, we've driven about 35.3 kilometers and gained 870 meters of elevation. Okay, so here are some selfies that Curiosity took. You can see a comparison between Sol 84 and Sol 3303. You can see the big difference, which is that Curiosity has actually collected a fair amount of dust. So you can see really how dusty and active the atmosphere really is. Okay, so how does rover operations work? Now, it takes about 15 minutes to send information from Earth to Mars. So typically what happens is we send this big set of instructions to Curiosity at the end of the day on Earth, which is the beginning of the day on Mars. And these instructions include information about like what targets each of the instruments on the rover should investigate, any kind of calibration activity or imaging activity, and any information about travel time and the direction and things like that. So now it usually takes about 7 hours for the science and operations teams on Earth to analyze the downlink, which is the information that the rover sends to us here on Earth. And then we synthesize a new plan and then prepare the next set of instructions for the rover. So my work with the rover concerns the downlink with KimCam, which is one of the instruments I'm going to discuss in a moment. And from this information, I write preliminary science reports on science targets and the images, and this also includes occasionally summarizing and presenting weekly results to the team as a whole. So as you see in this cycle, you sort of get all of this assessment, and then you work to make this plan. That you have you generate a sequence of activities, and you make sure that everyone is on board with the sequence that we want to use, and then you send all of that instruction up to Curiosity for the next day. Okay, so this rover is about the size of a car and weighs about 900 kilograms. And Curiosity is equipped with a drill, 2 laboratories, and 10 scientific instruments. So about the instruments on Curiosity. Going clockwise, we have, so starting from the middle here, we have RAD, the radiation assessment detector. So this one characterizes energetic particle radiation at the surface of Mars. And then next we have ChemIn, which is inside the rover. This stands for chemistry and mineralogy. This is a mineralogy instrument that identifies and quantifies minerals in the target rocks and soil. And it also has capabilities as a powder X-ray diffraction instrument and X-ray fluorescence instrument. Next, there we go, we have SAM, which is the Sample Analysis at Mars instrument suite. This is also located inside the rover, and it explores the molecular and elemental chemistry of targets, specifically pertaining to life. This is followed by DAN, which stands for Dynamic Albedo of Neutrons. These are active. This is an active passive neutron spectrometer that investigates the H and OH bearing materials in the surface of Mars. After this, we have MARDI, which is the Mars Descent Imager. And this one, what it does, it is meant to take images during the landing process, especially during the descent through the Martian atmosphere. Following MARDI is MALI, which it stands for the Mars Hand Lens Imager. This is a color camera that can change focus to the hand lens scale, and this is very helpful to identify minerals at the surface of Mars. Next, we have APXS, which stands for the Alpha Particle X-ray Spectrometer. This characterizes the geology that is surrounding Curiosity, and it has really high precision and very low detection limits. Next, we have the brush, the drill sieves, the sieves, and the scoop. Now, these are physical tools that help us to investigate the surface of Mars, so we can actually drill into the surface and we can investigate the drill tailings that result from these activities. And what we can do is we can collect a sample on a tray for MALI, APXS, ChemIn, and SAM to look at inside the rover. Next, we have REMS, which stands for the Rover Environmental Monitoring Station. Now, the purpose of this instrument is to assess the atmospheric parameters such as wind speed and direction, the humidity, and the temperature near the rover. After this is MASTCAM, which stands for Mass Camera. It's a 2-instrument suite of cameras that is used to study the geology of inside Gale Crater. And lastly is ChemCam, which stands for Chemistry and Camera, and it's capable of capturing images and doing bulk elemental composition analyses on targets. And I'm going to go into detail about this in the next slide. But all of these instruments, this is a huge international collaboration to deliver all of these payload instruments. And we've got like significant contributions from other countries such as France, which contributed a great deal on the construction of SAM and ChemCam. Now, ChemCam, here we go. So it's got 2 units. It has a mass unit, which is that image on the right-hand side, so kind of the head and the eyes of the rover. And this mass unit, it holds the laser, the telescope, the remote micro imager, or the RMI camera. And the body unit which is on the rover, it contains this optical demultiplexer that separates the light it collects to enter 3 spectrometers that cover the UV, the visible, and the near-infrared wavelengths. And it also contains other equipment such as the cooler and other associated electronics. And the technique that ChemCam uses is called laser-induced breakdown spectroscopy, so or LIBS. And so what this does is you have brief but really powerful laser pulses that hit a target, and then it ablates the atoms on the target into really excited states. And as these states decay, they emit light that is captured by the telescope in the mass unit, and then this is transmitted to the spectrometers. All right, so what kind of products can the instrument produce? Now, ChemCam can actually perform LIBS on the rock targets, such as in these 2 images here, and it can collect the images of these rock targets and long-distance targets as well, such as the one in the bottom shown here, which is called LD Deepdale 3573, and it was taken in 2022. So next, here's an example of LIBS spectra that ChemCam can collect. So these are results for the target coronation, which is ChemCam's first target on Mars. And what happens is that ChemCam shoots 30 shots, 30 laser shots per point on the target. And this plot itself that you're seeing is a composite of the spectra. And so what we see here in the spectra is we can see a slight enrichment of magnesium, for example, but note that this peak height doesn't necessarily correlate to the relative abundance of the element in the rock. But overall, for example, in this spectra, we're seeing that the preliminary analysis shows that it's a basalt. So ChemCam has made a lot of discoveries over the years, and one of the really recent ones is of elemental sulfur stones on Mars. So the rover actually crushed some rocks beneath its wheels, and when we looked back, we saw that it revealed these really high albedo stones, which you can see on the right-hand side there. And when ChemCam went back to analyze them, it was discovered that these rocks actually had really unusually high sulfur signals with no correlation to any other elements, which indicates that these stones are pure sulfur. And this is actually the first time that this mineral in its pure form has ever been found on Mars. So we've got many other discoveries also, and some other activities that we have done. We have done 49 solid samples that have been analyzed along the rover traverse. We've done 43 drill holes and 6 sample scoops. And these sample scoops are, as I mentioned, we collect a little sample in a tray on Curiosity that is sampled by APXS and Molly and Sam and Kemin. And we have also completed dozens of atmospheric samples, which has helped us to better understand the current atmosphere on Mars. All right. So one other discovery is long-chain hydrocarbons. So these are a very significant discovery on Mars. Actually, these are organic carbon-based molecules which were found in the mudstones in the plains of Gale Crater, which are thought to be part of ancient lake deposits. We have also found these organics in the mudstones that are along Mount Sharp as well. And now experiments with the SAM instrument actually determined that these molecules, specifically the decane, undecane, and dodecane molecules, have the highest molecular mass of the molecules identified on Mars to date. So while these complex organic molecules can also be produced abiotically, they're also products of biochemical reactions. So their presence on Mars is evidence that these molecules can be accumulated in ancient lake settings and then preserved for billions of years which really has some significant implications for the search for potential biosignatures on Mars. Now, another recent discovery is that of the carbonates in sulfate-bearing units on Mars. So Curiosity found enrichments of iron carbonate siderite along the Rover traverse. And comparing the analyses of these samples done by Chemin and Sam and KimCam, we found that the purity of these minerals is actually consistent with a formation scenario in which they form by precipitation out of the water. So this implies that the iron carbonate siderites could contain a reservoir of carbonate that's not accounted for when Mars still had a really dense CO2 atmosphere and also surface liquid water. So, but it was also discovered that this siderite can be dissolved. And this dissolution releases the CO2 back into the atmosphere. And this in itself is really significant because this means that it would be a crucial part of the carbon cycle on ancient Mars that may have regulated the climate. Okay, so we've also observed lots of physical phenomena, and this is one such phenomenon. These are dust devils, and these result as from strong atmospheric convection, and as they move, they pick up dust and they deposit it elsewhere, and so the erosion process continues on the surface of Mars. And here we've got these high altitude clouds. These are illuminated from over the horizon by the setting sun on Mars. And these clouds are made of either water or CO2 ice. And when you have very thin clouds with really small ice particles that are very similar in size, you have this iridescent effect as the sunlight is diffracted into all these different kinds of colors. So you see rainbow clouds on Mars. Now, what is Curiosity up to today? This year, we have reached this set of intersecting decameter scale ridge structures that's interpreted to be a boxwork structure. So we call them the boxworks. They are a network of fractures that are cemented by minerals precipitated from groundwater. And a sample drilled from these ridges will allow Curiosity to search for like an ancient habitable environment in the subsurface of Mars. So keep an eye out for that news. So just to illustrate with my mouse, here, these structures, these are all boxwork structures. So we're going through that now. So, all right. So we have lots of ongoing projects concerning Curiosity, so I'm really excited to tell you a little bit about my ongoing research. Now, along the Curiosity rover traverse, we've observed some really interesting diagenetic features that are enriched in phosphorus. So these two images on the right, if you'll remember from the earlier slide about the KimCam products, these are actually targets that contain phosphorus in them. So the one on the top is called Foteine. This one hit these dark-toned nodules, which are sort of diagenetic in origin. And then below we have the target Foteine, which is enriched in iron and phosphorus. Now, phosphorus itself is an element of particular interest because it's really an important biogenic element and it plays a significant role in prebiotic chemical processes. It also is really important to metabolic processes and also in chemical reactions involving DNA and RNA. So in addition, it's really heavily dependent on biotic activity here on Earth. So this raises the question, how does the phosphorus cycle work on Mars where it's an abiotic environment? and what could have led to these phosphorus enrichments that we observed with Curiosity, and how is the phosphorus mobilized and transported in this abiotic aqueous environment in early Mars. So to answer these questions, we want to quantify phosphorus in ChemCam spectra so we can better understand what processes could have controlled the phosphorus availability in Gale Crater, because those enrichments that I mentioned in the previous slide, they don't occur all over the traverse. They're quite rare. So to do that, we will complete a phosphorus calibration on ChemCam Libs, and we've got 2 testbed instruments here on Earth to match the one that Curiosity has on Mars. So one is located at Los Alamos National Lab here in New Mexico in the US, and the other is at the Institut de Recherche en Astrophysique et Planetologie, or IRAP, in Toulouse, France. And by using these test beds, we can apply the calibration to libs on ChemCam on Mars. So basically, the idea with making a calibration is you have a suite of rock samples or powder samples, in which you know the phosphorus concentration, or really the concentration of whatever element you are trying to calibrate to. And you do an analysis on all of these samples to create this calibration, and this will improve how we quantify the said element on Mars. Now, some perspectives, some takeaways. Curiosity is really a testament to how important rover exploration is to understanding other planetary bodies in the solar system. We have successfully sent rovers to the moon, to Mars, in asteroids, and one mission that's currently in the works that you might have heard of is Dragonfly, and this is in this image here. And the purpose of Dragonfly is to explore the surface of Titan, and it is at the moment scheduled to launch in 2028. So, another location that's also a good contender for rover exploration is Europa, which is one of Jupiter's moons. And this has a global ocean covered by an icy shell, making it this really intriguing target for planetary scientists and astrobiologists alike. So all in all, rover exploration is really key to understanding other objects in our solar system, especially at the surface, and conducting in situ experiments will give us a lot of insight into our past, like how all of these surfaces have formed, and we may even be able to find biosignatures in the past or even the present. So more to come. Thank you so much.
Okay, thank you for Foteine. So such an engaging talk. So it's exciting to hear how the Curiosity. So I think it's time for here's one question here. It's now the Q&A session. So, oops. Any question from the audience? No? Okay. 香渊六，盛元老师，OK， 盛元老师，你要自己提问题吗？你要开麦克风吗
？Yeah. Can you hear me?
Yes.
Yeah, we can hear you.
Okay, yeah, thank you for the nice talk. You mentioned about the discovery of the long chain hydrocarbons.
Mm-hmm.
I'm curious because the figure you showed seems to indicate that they are of comparable lengths in terms of that long chain. I'm curious whether you actually see a sequence of long chain hydrocarbons that at progressing length, or there's a specific size that survived under certain environments. Can you comment on that?
If I recall correctly, these are actually the longest ones that we have seen surviving on the surface of Mars. Maybe I can go back. There is a paper that was published this year. Here we go. Yes, Fresnit et al. That discusses the experiments that they did with the SAM instrument. So does that help answer your question?
Yeah. So it looks like they have the C10 to C12. So I suppose there are like C8 or even shorter ones that not highlighted in the discovery paper, but they all exist. That's my suspicion. Yeah. Thank you.
Okay, so any other question? I have two very basic questions, and we have seen the Curiosity self at the different times. You just showed, and over the year, the rover looks more and more covered by the Martian dust or the sand. So I'm wondering, does all this dust will cause any problem for the rover or the instruments?
Right. So let me go back so we can see those pictures. Where do we go?
Yep. Please.
Here we go. Okay. So yes, the dust is a bit of a concern. However, currently we are not experiencing any major difficulties with it. It is, however, just a general, because the rover is actually 13 years old. We just passed 13 years a couple of weeks ago. And it has far surpassed the original planned time for the mission. So really what we're concerned about is the wear and tear of the wheels. That is something to keep an eye out for. And of course, just instrument health as a whole. But yes, that is something we need to monitor as time goes on, is how much dust is getting collected on the rover.
Thank you. So the other question, and you have showed the drawing photo, the Curiosity drawing photo, and I think the material that comes out looks different, and some the rock or the sand looks like brown, like the surface, the brown color, and but some is more gray. Is that because the rock or the layer underneath the different?
Yes. So these are you referring to the KimCam product page?
Yep.
Okay, let me run there. We can have there we go. Okay. So the top two images here, they are colorized mosaics. And what KimCam does is it actually, the first 5 shots of the 30 lib shots clears dust away. So, however, most of it, so what we're seeing here in these 2 images, the color is actually because of the composition of the rock. So not all of it looks like that. We've seen ones that are like a pale, like red-orange color. We've also targeted meteorites, which are the really steely gray, but they're also kind of covered in dust. So it varies across different targets. Yeah.
Okay, I understand. So thank you.
Mm-hmm.
So any other question for the Foteine? So if there are no more questions, so let's once again thanks Foteine for there's a question or no? So let's once again thanks Foteine for today's talk, and please feel free to visit our TSU website to get the latest update for the upcoming events. So thank you all for joining us today, and we are looking forward to seeing you next time. And thank you, Foteine. Thank you so much.
Thank you so much for the invitation. Thank you.
Thank you. Goodbye.
Bye.